Our today's lecture is about force analysis on bevel gear. In our previous lecture, we have talked about bevel gears, its types. So, in today's lecture, we will be doing force analysis on spur gear, bevel gear, but it will be on straight bevel gear. So, let's understand it from the diagram. Here, this is the diagram of the pinion, and that pinion will be meshed with another bevel gear. So when that pinion rotates, the meshed gear will try to stop it from motion and exert force on the pinion. This is how this force will be exerted, and it is represented by W. This force is exerted in three-dimensional space, 3D. So we can resolve it into its components, and to understand it, let's draw a box that will help us to understand how the force is exerted in three-dimensional space. The back and the bottom faces are drawn by dotted lines. The force which is exerted on this bevel gear, which is pinion, is like this. These are the front and back face corner lines, which are in y direction or y-axis. This force is making an angle phi with the y-axis or y-face. Now we can divide this force into its rectangular components by two ways. One way is to start from the tail of the force exerted on this pinion and move down in y direction and then move in x direction. The angle between x and y component will be 90, and then move in z direction, and the angle here between x component and z component will be 90. This is the rule of head to tail rule. So if we sum up these rectangular components by head to tail rule, it will give us again the same force W. Another way is to start from the tail of the force W, move down in y direction to give us y component, and then when we get to the bottom face, meet this y component with the actual force like this. The height of all the faces are the same, so these two lines are equal to each other. So for better understanding, let's draw one component like this on the corner of the back faces. Since W has three components, so the other remaining two components we write it with single force component like this on the top face, or we can also draw it on the bottom face. This is the top face, which looks like a rectangle, and this is the bottom face, which also looks like rectangle. They have the same length and breadth or width, and this diagonal is equal to this diagonal. So if you write the other component, which is actually constituted from x and y component of the W, they are same, as the component in the y direction is actually tangent to this bevel gear, so we represent it by WT because it is the tangential component of W, and the other two components are represented by one component on the bottom face like this. Let's name the second component as F. If we want, then we can divide this F component into its further rectangular components. This is the component which will be along the radius, so name it as WR because it is along the radius, and the other component will be parallel to the shaft axis, so it is named as WA because it is axial component. The axial component is also called thrust force. The angle between the force F and its component WR is gamma. As we told you in our previous lecture that this gamma angle is equal to half of the cone angle, of the pinion. Now let's talk about how the angle between F and WR is equal to gamma. As bevel gear is like a cone, this is how we can draw the cone of this gear in 2D. And this gamma is actually the half of the cone angle. Now let's draw a parallel line to the shaft axis like this. Since this line is parallel to the shaft axis, so the angle with this line will also be equals to gamma. So draw a perpendicular line on this line and draw a perpendicular line on this line as well. So both of them will make 90 angle with the lines upon which they are drawn. So when you rotate both of these lines with 90 degree, then this line will get over here and this line will coincide with this line. So we can say that the angle there is also gamma. So W is divided into WT and into F, and F is further divided into its rectangular components WR and WA, and the angle between WR and F is gamma. Since bevel gear is like a cone, so its radius is not constant. Let the distance from the center up to the top face of the teeth from the front is R1, and the distance from the center to the top face of the same teeth which is at the back or from back view or as R2, and the force exerted on this pinion is neither at R1 nor at R2. It is at this point which is in between R1 and R2. So if you add R1 and R2 with each other and divide it by 2, it will give us its average, and the force is also exerted over the radius R average. Wt is equal to torque divided by R average, and as we know that torque is equal to R cross F. Here in this case, the force that is responsible for the producing the torque in the shaft or in the gear is actually Wt. So replace F by Wt, and R here is equal to R average because Wt is exerted at R average, and rearrange the formula for Wt. So Wt is equal to T by R average. Now the radial component WR is equal to Wt tangent of pi into cos gamma. To prove it, let's take tangent of pi, which is equal to perpendicular by base. Here W is the hypotenuse and Wt is the base, and F is perpendicular. So multiply Wt on both sides, we will get Wt tangent of pi is equal to F. Now look at the bottom face of this box where we have angle equals to gamma and WR and F. Now cos of gamma equals to base by hypotenuse, so cos of gamma equals to WR divided by F, because WR is the base and F is the hypotenuse. For this, rearrange it for F, so F equals to WR by cos gamma. Multiply cos gamma on both sides, we will get WR equals to Wt tangent of pi cos gamma. As we proved the formula for WR, so let's get back to the previous equation, that was Wt tangent of pi equals to F. Now take sine of gamma equals to perpendicular by hypotenuse. Perpendicular is WA, so replace it by WA and hypotenuse as F. So sine of gamma is equal to WA by F. Again rearrange it for F, which will be equals to WA divided by cos of sine of gamma. Now multiply the sine gamma on both sides, we will get WA equals to Wt's tangent of pi into sine of gamma. These are the main forces that play an important role in force analysis. We should also have some knowledge of the geometry as well to have complete picture of the force analysis on spur gear. To understand it further, let's have an example on this, which is 13.8. Here in this example we have a pinion which is meshed with another bevel gear. The formulas that we proved previously were for the forces on the pinion. Here in this example, the pinion is rotating with 600 rpm. The direction of the pinion rotation is shown. This is how it rotates, and it transmits 5 horsepower to the gear. Bearing A and bearing C, this bearing and this bearing are actually taking the thrust load or axial load. What we will have to do in this problem is to find the reactions on the gear shaft. These distances are used in the calculation, so you should remember it. The force is exerted at the point G. This is R1, this is R2 radius, and the distance between the central axis of the gear shaft to the point G is equal to R average, which is 3.88. Since the pinion is rotating like this, so at the point G, the WT force on the gear will be exerted such that it will be out of the page or out of the screen of the laptop or mobile, and that axis is taken to be Z. Positive Z axis is taken out of the page and negative Z axis is taken into the page. WR will be along the radius, and since bearing C is taking the thrust load, so thrust load should be against the bearing C. So WA is in negative y direction. Now let's draw its free body diagram. This is the x-axis, this is the y-axis, and this is the z-axis. Shaft was in along the y-axis, so this is the shaft. These are the bearings D and C. This is the average radius of gear 3, means gear where the force was exerted on the gear at point G. The distance from point D to the origin is 2.5, as I already told you to notice it in our previous slides. And from origin to this point, it is equal to 1.293, and from this point to G, which is our average, equals to 3.88. Now if you want to move from point D to G, you can directly move by drawing straight line from D to G, or you can move like this as well. Let's draw the straight line between D and G. Name it as DG or RG. If we want to write it in the form of position vector, it will be equals to 3.88 I, because we are moving in I direction, means positive x direction, minus 2.5 plus 1.293 in z direction. Here we have put minus sign because we are moving in negative y direction. So note it down because we will use this position vector RG in our calculations. And the distance between the origin and C point is equal to 3 into 5 by 8. And from D to C, let's represent its position vector by RC, which will be equals to 2 into 1 over 2 or 2.5 plus 3 into 5 by 8 whole multiplied by minus j. So note it down too. Now draw the forces at point G. Since we already talked about the tangential component, that it will be in positive z direction, so let's draw it in positive z direction, and the axial component WA will be in negative y direction because C is actually taking the thrust load. WR, so the WR is in a radial direction or negative x direction. There will be reactions at bearing D and C which will be taken by them, so show them as well. At D as it is in x direction, so we have written it as FDX, and this is in z direction, so FDZ. These are the actual directions of FDX and FDZ, but in our calculation we will take these forces in positive directions, and after the calculation we will come to know that these forces were actually in negative direction, so that is why from now we have written it in negative directions. This is not FD, it is FDZ. At point C, take FCX and FCZ in positive directions and FCY also in positive direction. The forces at D and C, you can represent it in any direction, but later on in the calculation you will find its exact directions. So if you take it in wrong direction, it will just give you the negative answer, and the negative sign will show that the direction you have taken is wrong. Its exact direction is opposite to that you have taken. This is the torque T exerted on the gear shaft. Now let's solve this problem. First of all, we will try to find out gamma and capital gamma. Tangent of gamma equals to np divided by ng. Now multiply module m in numerator and denominator, as m into n equals to diameter d. So tangent of gamma equals to dp divided by dg. From the diagram we can see that dp equals to 3 and dg equals to 9. So put these values and take its tangent inverse. We will get 18.4. The same way capital gamma equals to tangent inverse of dg divided by dp, which is equal to tangent inverse of 9 by 3. That will give us 71.6 degree. Now pitch line velocity, as we know that v is equal to r omega. Here r is r average and omega is equal to 2 pi n. If r is given in inches, then divide it by 12 to get velocity in feet per minute. If r is not given, d is given, then 2r equals to d. Then v will be equals to pi dn by 12. Here r is given, which is 1.293 and n equals to 600 rpm. So put these values, we will get v equals to 406 feet per minute. Now the tangential force, it is equal to T by R average. We also know that power transmitted, which is represented by H, is equal to F into V. Here the force responsible for the power transmission from one shaft or gear to other shaft or gear is equal to Wt. So H equals to Wt into V. So Wt is equal to H by V. If power is given in horsepower, then replace horsepower by 550 lbf into feet, and velocity will be equals to feet per minute. So instead of minute, replace it by 60 seconds. So 60 will come up to the numerator, and 60 multiplied by 550 equals to 33,000. So Wt is equal to 33,000 H by V, as H is 5 horsepower and V is 406 feet per minute. So put these values, we will get Wt equals to 406 lbf. Previously we derived formulas for Wa and Wr, but those forces were on pinion. Now as we are about to find these forces for the gear, so replace the angle gamma by capital gamma. So Wr equals to Wt tangent pi cos capital. Wt is 406 and pi is 20 and capital gamma is 71.6. So put these values. So Wr equals to 46.6 lbf. Similarly, Wa equals to Wt tangent of pi into sine of gamma, means capital gamma. So put these values, we will get Wa equals to 140 lbf. Wt was in positive z direction, Wr was in negative x direction, and Wa was in negative y direction. For taking the moment at the point D, we have already obtained the position vector of dg, which was represented by rg, which is equal to this. Similarly, we have also calculated the position vector of rc, which is this. Now summing the moment of all the forces, so rg cross w plus RC cross FC plus TJ. This is RG. WT was 406 and Z positive Z direction, and WA was 140 in negative Y direction, and WR was in negative X direction 46.6. This is RC. This is FC. All of its components were initially taken to be in positive directions. This is the torque which is taken to be in positive Y direction, and it is the torque, it is the shaft. The torque was written like this. Now from right hand rule, curl your fingers in the direction of rotation. The thumb will show the direction of the torque, so it is in positive Y direction. Now we will have to find the cross product of these two. Write IJK, write the values of RC. Then here the K component is 0, so instead of the third component, which is K component, write 0 over there in the determinant. Then write the force values along with their signs. Expand their determinant across the first row. So first of all, write I into determinant of these values minus J into determinant of these values, K into determinant of these values. This is how we will write it. I into multiply these two values minus multiplication of these two values minus J into multiply these values minus multiply these values plus K into multiply these values minus multiply these values. Then cross product of RCFC, write IJK, then write RC value whose I and K equals to 0, then write FC value which is FCX, FCY and FCZ which is equal to, expanding it on second row, so I and K component will get equals to 0. The 0 and respective determinants will be equals to 0. So we are left with I was taken positive, J was taken negative, K was taken positive. This will be taken negative, this will be taken positive, and this will be taken negative. So it is equal to minus 6.125 into I, K, f of cx and f of cz. So minus 6.125 into this multiplied by this minus this multiplied by this. So from this we will get this minus 1540i. From this we will get minus 1575j, and from this we will get minus 720k, and from this we got this plus tj equals to 0. Now take I component equals to 0, that is minus 1540 minus 6.125 into f of cz. Move this term on the other side and divide 6.125 on both sides. We will get f of cz equals to 1540 divided by minus 6.125. Now compare j component. So tj equals to, in fact he equals to 1575. Comparing k components, so minus 720k plus 6.125 into f of c x equals to 0. Now move 720 to the other side of the equality, so we will get 6.125 f of c x equals to 720. Then divide 720 by minus 6.125, that will be equals to f of c x. So t equals to 1575 lbf into inch, f of cx equals to 118 lbf, f of cz equals to minus 251 lbf. So the direction that we took for f of cz was wrong, it is in negative z direction. Now we have to find forces at d and f of cy also. Now either take forces in x direction equals to 0, y direction equals to 0, z direction equals to 0, or sum these forces by writing them in the rectangular components, and then take all I components equals to 0, j components equals to 0 and k components equals to 0. So we have to find f of cy and also f of d components. All other values are known now, as we have told you earlier that we have taken the true direction of the f of d components in the diagram, but here in the calculation we will take them in positive directions. and after the calculation we will definitely get its values to be negative, so that is why from the start we have shown their true directions. Now take I components equals to 0, so f of dx equals to minus 118 plus 46.6. Now j component equals to 0, so f of cy equals to, which is equal to 1/4, and then k component equals to 0, so f of dz equals to, so for f of c these two components were already calculated, and here we calculated f of cy, which is equal to 140. So write f of c in its rectangular component form, and when you calculate these two values, so f of dx equals to minus 71.4 and f of dz equals to minus 155. So f of dx equals to minus 71.4 and f of dz equals to minus 155. So f of d equals to f of dx plus f of dz, is f of dx equals to minus 71.4 and f of dz equals to minus 155. So write them along with their unit vector. F of d equals to minus 71.4i minus 155k.